In this lesson, we're going to do an example on finding the tangential and normal components of acceleration for a vector function. Recall that if our acceleration vector, a, is to be written as the tangential component of acceleration a sub t times t plus the normal component a sub n times n, then a sub t is the derivative with respect to t of speed, so the derivative with respect to t of the magnitude of velocity. And the normal component of acceleration we can find using our equation. A sub n is the square root of the magnitude of a squared minus a sub t squared. And remember, this came from figuring out that a dotted with a, which is the length of a squared, is equal to a sub t squared plus a sub n squared. So we were able to use that equation to solve for a sub n. So the point here is that once we have the acceleration vector a and a sub t, we can use that to find a sub n. So let's do an example. Here I've given you the vector function r of t as cosine t sine t t squared. And again, we want to be able to write our acceleration vector as some number times the unit tangent vector plus some number or scalar times the unit normal vector. So the first thing we're going to do, let's go ahead and find our velocity and our acceleration vectors. So velocity is just the derivative of position. So taking the derivative, we get negative sine t, cosine t, and 2t. And we also note that we're going to need the magnitude of that vector, so the speed. So let's go ahead and find that. So we're going to get the square root of negative sine t squared plus cosine t squared plus 4t squared. Sine squared plus cosine squared gives us 1, so we get the square root of 1 plus 4t squared. Now next, let's go ahead and find our acceleration vector. So our acceleration vector is just the second derivative of position or derivative of velocity vector. So we get minus cosine t minus sine t 2. So we now have our acceleration vector, and remember our goal here is to be able to write this vector in the form a sub t times the unit tangent vector plus a sub n times the unit normal vector. And we'd like to be able to do this, if possible, without having to come up with explicit expressions for the unit tangent and the unit normal vectors. Now a sub t we know how to do. So a sub t, remember, that's the component of acceleration in the direction of the unit tangent vector, so that's the derivative of our speed. We already found our expression for speed, so we just get 1 over 2 root 1 plus 4t squared. Chain rule says times the derivative of the inside, which is 8t. So simplifying, this gives us 4t over root 1 plus 4t squared. So that is our tangential component of acceleration. And now we can use our equation. A sub n is square root of magnitude of a squared minus 8t squared to find our normal component of acceleration. So magnitude of a, so magnitude of our acceleration vector, gives us square root of negative cosine t squared plus negative sine t squared plus 2 squared, or 4, which gives us root 1 plus 4, which is root 5. So this finally now tells us that our normal component of acceleration is the square root of magnitude of a squared, so we get 5, minus a sub t squared, so we get 16t squared, over 1 plus 4t squared. So what this tells us finally is that our acceleration vector, which, remember, we found to be minus cosine t minus sine t 2, so our acceleration vector minus cosine t minus sine t and 2 can be written as 4t over root 1 plus 4t squared times the unit tangent vector plus the square root of 5 minus 16t squared over 1 plus 4t squared times our unit normal vector. And again, the nice thing about this expression is that we've now written acceleration in terms of tangential and normal components, and we didn't have to find formulas for t and n separately. So now let's do an example with numbers just to see how this works out at a particular value of t. So let's see what happens, for example, at t is equal to pi over 2. So acceleration at time pi over 2 is equal to minus cosine of pi over 2. So that's 0, minus 1, 2. And plugging in for our tangential component, I get 4 times pi over 2. So that's going to be a 2 pi in the numerator over square root of 1 plus t squared is pi squared over 4. Multiplying that by 4 gives us pi squared in the denominator. So we have 2 pi over square root of 1 plus pi squared times the unit tangent vector. And then for our unit normal vector, we get this, our normal component, we get root 5 minus, again, t squared is pi squared over 4. Multiplying that by 16, we get a 4 pi over 1 plus pi squared, all times n. So at the point corresponding to t equals pi over 2, our tangential component of acceleration is 2 pi over root 1 plus pi squared, and here is our normal component of acceleration. So the key steps here are to first find your velocity vector and then the magnitude of your velocity vector. You want to do that because that's how you're going to get your tangential component of acceleration. You find your acceleration vector, and then using the magnitude of the acceleration vector, we can then find our normal component of acceleration. And if we want to do this at a particular value of t, we just take the expressions that we found and plug in that value of t.